and start from the current slide. So we actually are going to back up and go one more back. Not slide back, but we're going to go to do the vocabulary at the end of 4.8. But before we do, let me just go over the announcements. You've heard them all before. Math team's looking for you, okay? You're going to be ideal candidates for it. They meet Fridays at noon on the Birmingham West Campus, room C100. That's in the Science Building, C Hall, C100. And then Monday afternoon at 3, same place, okay? And then tutoring, if you need it, it's there, but you should be providing it. Y'all are good students. You should seriously consider tutoring. They'll pay you pretty reasonable money. You can work your own hours. It's a really good setup, okay? And you'll be helping students. And believe it or not, you'll be helping yourself probably more than you help others, because how I learned math the best was having to explain it to somebody else. That's when you really learn it. And you go, oh, yeah, okay, I understand what's going on.
If you haven't learned it, how can you teach it to someone else?
Well, what I'm saying is you can kind of memorize and fake your way through it, but to teach it to somebody else, you really have to know it. You know, I've seen enough people guess right on a test or on a quiz or something like that, but then they can't really tell how they got that, you know. In fact, I've had them come say this. I know I got the same answer in the back of the book, but I don't know how I got it, or something like that. Whereas if you're explaining it to somebody, you've got to know how it happened, you know. So I think there's what they call different levels of learning. There's surface learning and deep learning. I think that to help someone else with it, you develop deep learning. That's what I would say. I don't know if that makes sense or not. The one other announcement I wanted to make is, this one I especially wanted to have on the recording, is that I have an infusion tomorrow, so I will not be on either campus tomorrow at all. I think I'm there for blood work at 6. Infusion starts at 7 or somewhere around then, and I'll probably be there most of the day. So no way I'll make it back to campus at all. All right, so who knows what next week's going to be like. Hopefully it won't be so bad. All right, any questions on anything we've done so far? And all of you got your second test last time, right? Yeah, okay. I haven't sent it to the other. I gave it to one person, but I haven't sent it to the other one, so I've got to get that sent today. But where we left off, we had not quite finished 4.8. We don't have a slide on it, but it's the vocabulary at the very end of the section. On page 334, 4.8 vocabulary. A blank measures the acute angle that a path or a line of sight makes from a fixed north-south line. A bearing, exactly. Number 2, a point that moves on a coordinate line is in simple blank blank when its distance d from the origin at time t is given either by d is equal to a sine omega t or d is equal to a cosine omega t. Simple blank blank. Harmonic motion, excellent. Number 3, the time for one complete cycle of a point in simple harmonic motion is its blank, period, and the number of cycles per second of a point in simple harmonic motion is its frequency. Excellent, excellent. And we already went over the homework assignments in that section, didn't we? Seems like we did, but if not, you know about what they are. Okay, the chapter summary at the end might have some help for you when you're doing your test. The review questions may have help for you when you're doing your test. And the chapter test at the end may be helpful when you're doing your test. There is a little thing on proofs in mathematics on the Pythagorean theorem. And from what I understand, it's probably the most proved theorem in mathematics history, okay? People, just tons of people have have developed proofs for this. One U.S. president came up with a unique proof for it. Not our current one. Okay. James A. Garfield, the 20th president of the U.S., developed a proof of the Pythagorean theorem in 1876. And the one shown in the book, I think, is his. So you certainly are welcome to see that. There is also some problem-solving exercises on page 345 and 346. Okay? Any questions? Chapter 4 at all? Okay? Then we're going to start today with chapter 5, analytic trigonometry. All right? Now, 5.1 is using fundamental identities. Okay? Now, we have gone over and hit the identities, the very simplest identities, several times when we did unit circle, when we did right angle trig, and they've shown up several places. We're going over them again. Hint, pretty important stuff, huh? Now, of all the chapters in trigonometry, the one on identities is probably the ones that either people love or they hate. I mean, it's not a very neutral chapter, okay? It's pretty much fun, I think, most of it, but a lot of people don't like it at all. But anyway, we'll be using the fundamental identities in 5.1. So our objectives here are to recognize and write the fundamental trigonometric identities, and then we'll use those fundamental identities to evaluate trigonometric functions, simplify trigonometric expressions, and rewrite trigonometric expressions. And as we go on in this chapter, we'll be doing way, way, way more rewriting, but at the same time simplifying. The evaluating sort of gets left in the dust here a little bit, though we do some of that as well. Now, I don't know why my head is clogged up today. It hadn't been being, but suddenly this morning it is. I don't know if the air blowing out, I don't know what it is. Maybe the fact I was sitting here static and with the hair blowing on rather than moving around like I usually do. I don't know. So anyway, introduction to 5.1. We will learn how to use the following identities the fundamental identities to do the following. And this basically is restating what we just said. Evaluate trigonometric functions, simplify trigonometric expressions, okay? Develop an additional trigonometric identities. Not that you'll ever use them that much, but you can develop them and solve trigonometric equations, okay? So, here are our fundamental trigonometric identities. Like I said, you've seen most of these before, okay? Maybe not all at the same time. Generally, you see the top part here over and over and over again. So let's go over them again. The first they call the reciprocal identities because the trig functions each have a reciprocal function. So that's what these are. Sine is the reciprocal of cosecant. Cosine is the reciprocal of secant. Tangent is the reciprocal of cotangent. Cotangent, of course, is the reciprocal of tangent. Secant is the reciprocal of cosine. And cosecant is the reciprocal of sine. Those are your reciprocal identities. Hopefully you have those all well in hand right now. Then, these are called by a couple of different names depending on the text you use. This book calls them the quotient identities. I'm used to seeing them referred to as the ratio identities. Okay? The tangent is the ratio of sine to cosine, or the quotient of sine to cosine. And the cotangent, of course, then would be, because it's reciprocal, is the ratio of cosine to sine. Those are our two quotient or ratio identities. Now, these are just three expressions of the Pythagorean identity. Here's the one that's the fundamental one. sine squared u plus cosine squared u is equal to 1. No matter what u is, okay? The square of the sine of any angle plus the cosine of the square of the same angle is going to be 1. Always. Always. Pythagorean identities. Okay? And the next two you get simply by dividing. I think we've done this before, but in case you've forgotten, let's just do it real quickly. To get the second of these, let's divide, well, let me get my pen color back. Okay. Let's divide everything on the first identity by cosine squared u. Cosine squared u. Cosine squared u. And what's sine squared over cosine squared? Tangent squared. Okay? And what's cosine squared over cosine squared? 1. And what's 1 over cosine squared? 1 over cosine squared. 1 over cosine is? Secant. So it's secant squared. So what do we have? Tangent squared plus 1 is secant squared. They wrote it the other way, 1 plus tangent squared is secant squared. There's another identity you get just by dividing by cosine squared u. Of course, okay, now let me just say this. This first one, sine squared u plus cosine squared u is equal to 1. That's good for any value u, any angle u. This one obviously is not. Why? It's not valid for anywhere that cosine is equal to 0. If it were, we just divided by 0. Can't happen. So this is valid anywhere where cosine is not equal to 0. It's not valid where cosine is equal to 0. That's why tangent of 0 is not, tangent of certain angles is not defined. Your half angles are not defined. Half pies are not defined. And secants, of course, then could not be defined at your half pies because that's where cosine is 0. Now, should be no mystery how you got the next one. What you think? Yeah, divide by sine squared u. Okay? I'm being really lazy today. And that's sine squared u, and sine squared u. And what's sine squared over sine squared? 1. What's cosine squared over sine squared? Cotangent squared. And 1 over sine squared? Cosecant squared. Okay? So that's where you get the second. 1 minus cotangent squared u is equal to cosecant squared u. Now, like I said, these are just the 3 most common ones. You can rearrange these all kinds of ways and use the same identities to say other things. Okay? For instance, you can subtract the cosine squared from both sides here and have sine squared is equal to 1 minus cosine squared. Right? And then you can take the square root of both sides and have sine u is equal to plus or minus the square root of 1 minus cosine squared. And then you could subtract sine squared from both sides and have cosine squared. So you can do that. Then you can take the square root there. Over here, you can subtract 1 from both sides and have tangent squared is secant squared minus 1. Or you can subtract secant squared from both sides and have 1 minus secant squared is equal to, well, that's about saying the same thing. And then, but you can take square roots, you can do all sorts of things there. And the same with the last one. You can subtract 1 from both sides, or you can subtract cotangent squared from both sides. So there's lots of ways you can rearrange. Okay. Now I'm going to erase that just because it looks ugly. But those are just other ways you can express this Pythagorean identities. Now, we talked about this one. We don't really use them that much, but they certainly are there. They're the cofunction identities. Okay? We know that the sine of the complement of u, because if u is an angle, pi has minus u is the complement of that angle, right? So sine of the complement of angle is the cosine of the angle. That's where the co comes from, the complementary angle. Okay? And similar then, the cosine of the complement of u is the sine of u. The tangent of the complement of u is the cotangent u, where the name comes from. And the cotangent of the complement of u is tangent u. Secant of the complement of u is cosecant u, and the complement of cosecant of the complement of u would then just be the secant. Okay? Again, those are all true, we just don't use them a lot. Okay? We use those others all the time. I mean, just all over the place. Now, the even and odd identities, again, they can be used in analytic trig, just not usually used that much. This is just things to know about. The sine of the negative of u is actually the negative of sine u. Why is that true? Sine is a what kind of function? Odd function. But cosine of negative u is the same as cosine of u. That's because cosine is an even function. Tangent of negative u is the opposite of the tangent u. That makes it odd. Okay? And then the reciprocal functions follow the same pattern. Because cosecant is reciprocal of sine. The cosecant of negative u is minus cosecant u. It's odd also. Secant is reciprocal of cosine. Therefore, the secant of negative u is secant u because it's also odd like cosine is. And the cotangent of negative u is the negative cosangent of u because it's an odd function because it's reciprocal of tangent. So 4 out of 6 are odd functions, only the cosine and its reciprocal secant are your even functions. All right, those are the basic identities, okay? The fundamental trig identities. We're going to use those like crazy, especially those top half and maybe a little bit of the bottom. Now, we will use some of those others, especially at the bottom, when we're developing other identities. Okay? And that's going to be in the second part of this chapter. So, Pythagorean identities, like I mentioned before, I'm having trouble breathing, are sometimes used in radical form, and this is what I said before. Remember, sine squared u plus cosine squared u is equal to 1. Subtract cosine from both sides. Sine squared u is equal to 1 minus cosine squared u. And then take the square root of both sides. Sine u is equal to plus or minus 1 minus cosine squared u. Or this one that was tangent squared u plus 1 is secant squared u. Subtract 1 from both sides. Then take the square root. And tangent u is plus or minus the square root of secant squared u minus 1. Now we'll use those. Well, we won't use them much. You're going on to calculus, right? The two of you? No. Okay. Once we get into calculus, we'll use these kind of things a bit more frequently. That's one reason we're hitting them now. Now, you may have a problem here, don't we, Houston? How can sine u be either plus or minus? That would indicate it's hardly a function. Well, depends on the value of u. If u's in the first quadrant, what do you know that, which one do you use? Positive. Well, the trig functions are positive in the first quadrant. In the second quadrant, which would you use? Positive, because sine is positive in the second. All students take calculus, right? Except you two. Okay. But then in the third quadrant, if U is in the third quadrant, we'd use the minus. And then the fourth quadrant, we'd use the minus. So it depends on where you are. That's why it says the choice of U. No, it depends on where U is. U is or you are. No. All right. It's just how, where U is located and which quadrant. That will determine which side you use. Okay. That's not very fair of them. Oh, no, it is. Okay. Now we're going to use these fundamental identities. We're going to start fairly simple and move on from there. One common application of trigonometric identities is to use given values of trigonometric functions to evaluate other trigonometric functions. Okay? And here is example 1. Now, and there's several ways to do this. You use whichever way makes the most sense to you. Here's what they give you to begin with. Secant U is equal to negative 3/2. Okay? Now, I'm a cynic, okay? Before I'm going to swallow that hook, line, and sinker, I ask myself, does that even make sense? I thought the trig functions had to be between plus and minus 1. Is that true? For values. Only sine and cosine have to be between plus and minus 1. In fact, what is secant and cosecant got to be? Outside of plus or minus 1. And that certainly is below minus 1. Okay, so sure enough, that makes sense. Okay? So they've told us that secant U is equal to minus 3/2. That's a legitimate value. All right. Now they tell us one other thing. Tangent U, same U, okay, tangent U is greater than 0. What does that mean? What's another way of saying that? That's positive. It's greater than 0, right? Positive. Okay. Now, it says, use those two facts to find the values of all 6 trigonometric functions. Is that possible? Sure it is. Okay? Now, let's go back to that secant U being negative 3/2. That indicates, number one, that's a legitimate value, but it also indicates possibly what U can be. Can U be in the first quadrant? No, because everything's positive in the first quadrant. So we've just eliminated the first quadrant. Can U be in the second quadrant? Yes, because cosine is negative in the second quadrant, therefore secant would have to be. How about third quadrant? Yeah, cosine is negative there too. If you think about cosine curve, it starts at 1, that's positive, then it goes to 0 at pi half, right? 90 degrees. And then it goes negative to pi and back up to 3/2 pi. So it's negative all in here. That's the second and the third quadrant. But then it goes positive again in the fourth quadrant. So that tells us U is where? Either second or third quadrants. Exactly. Now, that little bit of information about tangent U being positive, what does that tell you? Where is tangent U positive? First quadrant, of course, but we know it can't be in the first quadrant because secant was negative there. Okay? Tangent is negative in the second quadrant, so secant U can't be in the negative quadrant. How about the third quadrant? Tangent is positive there, secant U is negative there, so those two pieces of information tell us we're in the third quadrant. Okay? So that's helpful. Okay? Now, I know how they want you to do this. Okay? But let me just tell you, to me, it's so much easier to draw a circle. Now, what kind of circle you think I'm going to draw here? A what? let's go with a 3 circle, because remember what secant is? Say again? A little louder.
Greater or less than 1.
Okay, it's greater than +1, less than -1. Yeah, we've already established that. But I mean in terms of opposites, adjacents, and hypotenuse. Hypotenuse over adjacent, perfectly. Okay, and what is hypotenuse always? Positive and the bigger number too, right? Ha ha ha, okay. That means that we need a, what kind of circle? A 3 circle. Okay, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I don't draw very good circles, so bear with me. Okay, there's a 3 circle. Okay? So if the 3 is positive, because that's the hypotenuse, always positive, that means the 2 has to be negative. So, and 2 is adjacent, so that's the x value. You go left on 2. You could go up or down, but since tangent is positive, we'll go down. So there we are right there on the 3 circle. Okay? The adjacent side is -2, and the hypotenuse is equal to 3. Okay? Now, I'm going to write down all the trig functions. Sine u, cosine u, tangent u, cotangent u, secant u, cosecant u. That's how I like to write them anyway. They've told us what secant u is. That's -3/2. It says to find the values of all 6 trig functions. I found that one. They gave it to me. Okay? That was pretty easy, huh? Now, what's the next easy one to do? Cosine. Because what's cosine? Say again? -2/3, because it's reciprocal of cosecant. You just use the reciprocal identity to get that, didn't you? Okay? Now, what do we do next? Say again? All right. Now, I'll tell you 2 ways to do it, and they are equivalent, but frankly, to me, they're better than equivalent. It makes sense, okay? Now, don't trust my circle. Don't say, oh, that looks like the y is a -2. I almost guarantee you it's not, okay? It's that my circle isn't very circular there, okay? But what we do know, if this is 2 units this way, and this is 3 units that way, can we figure out what the opposite side is? How? Pythagorean identity, theorem, okay? And what would that be? We're now looking for, can I call it opposite? Is that okay with you? So don't think that's a 0, that's an O. The opposite side is, or how would you do it? Do it any way you want to. We'll do something. Aha. Okay, you said it's the square root of, okay. Let me back up. I say you can do it any way you want to. Now I want you to do it my way, okay? No, I'm just kidding. I'm going to coach you a little bit here, okay? What is the Pythagorean theorem in terms of opposites, adjacents, and hypotenuse?
Hypotenuse is it either or, adjacent or opposite first?
It doesn't. Yeah, that doesn't matter.
Opposite
Opposite
squared
plus adjacent squared equals hypotenuse squared. That's what we need. We're looking for opposite, right? We know adjacent. So opposite squared will be, what will you do here? Subtract adjacent squared from both sides. So that's going to be hypotenuse squared minus adjacent squared, right? And we know those. So the opposite is going to be either the plus or minus square root of the hypotenuse squared minus adjacent squared, right? And guess what will determine our sign? Where we are, exactly. And you can look at it and tell me what's the sign of opposite is going to be. Negative, okay, because down in the third quadrant, where tangent is positive, okay? All right, so this will be minus the square root of, and what's the opposite? The hypotenuse? 3, square that, and you get 9 minus, what was the adjacent? Negative 2, but when you square it, it becomes a 4, so 9 minus 4, so that's going to be minus the square root of 5. That's what you told me before, wasn't it? Oh, was it? Okay, I couldn't hear. Huh?
I should say negative.
I can't hear.
I didn't say negative.
Oh, you didn't say negative. Okay, all right. Sorry about that. I just didn't hear. I thought you were saying a different number. Okay. So we now know the opposite. Okay? So what can we now write down? What depends on the opposite? I even put a sine. And what would sine be then? Minus root 5 over 3. And now that you know that, which other one do you know? The cosecant. And what would that be? Negative 3 over root 5. Now, sometimes they don't like putting radicals in the denominator, and sometimes they don't seem to care. If they did care, how would you express that? Negative 3 root 5 over 5. Okay, either one of those will be acceptable. Okay, we got 4 out of 5. No hope on the next one, right? Oh, we can. How would we get tangent? Opposite over adjacent, which is? Say that again. Over. So negative over negative is? Positive! Yay! There it is. It's positive. So that's root 5 over 2, which you could also do as sine over cosine. Just draw a line here. The 3's multiply out, and the pluses, the minuses go out, and root 5 over 2. Yeah, there it is. Oh, but we can't get cotangent, can we? What is it? 2 over root 5, but if you don't like putting radicals in the denominator, that could also be expressed as 2 root 5 over 5. Any one of those will do. Now, they didn't want you doing it that way. Okay? Oh, the first part, once they gave you secant, getting cosine, that's exactly how you were supposed to do it. Okay? What we did with the Pythagorean theorem, they really wanted you to do with the Pythagorean identity. And here's what I mean by that. Because we figured out what the sides were, which to me is the easy way to do it. What they wanted you to do is, we know cosine, right? We just got it from here. And then say that sine is 1 minus, the square root of 1 minus cosine squared, which you put, if you have a plus or minuses there, you know it has to be minus because it's in the third quadrant. And you do it that way. And it's perfectly correct. But it's just a little more work. And I'm lazy, okay? But you can do it that way, okay? And then, like you did, you went opposite over adjacent was tangent. They wanted you to do sine over cosine, which I said you can do the same way. And it's just about as easy, okay? Roy was a little easier. And then cotangent from tangent, and cosecant from sine. Reciprocal identity. So except for that one, they use the Pythagorean identity rather than the Pythagorean theorem. That's why it's called Pythagorean. We did it. And we got the same answer, so we're okay with it. Or I am anyway. Okay, to erase. Okay, does it make sense? Okay. So let's see what they do first. Using reciprocal identity, yes. That cosine u is 1 over secant u. That would be 1 over the negative 3/2. Well, you call it a reciprocal identity. Why don't you just take a reciprocal? That's minus 2/3. I wouldn't have done that middle step, but they did. It's correct. Everything's fine. Okay? Now, and like I said before, the next step, they use the Pythagorean identity rather than the Pythagorean theorem, which I thought was a little easier, that sine squared u is equal to 1 minus cosine squared u. Just subtract the cosine squared u from both sides. Okay? So then, since you know cosine u already, you plug that in. What is this thing squared? Cosine squared. Minus times minus is plus. 2 squared is 4 over 9. Right? And 1 minus 4 over 9 is 5 over 9. Exactly. Okay? And then, so sine squared is 5 over 9. So sine is square root of 5 over square root of 9. What's square root of 9? 3. So you got your square root of 5 over 3, but you have the plus or minus, and since sine is in the third quadrant, it's going to be the minus. So minus square root of 5 over 3, which is exactly what we got. I think our way was easier. Don't y'all? Okay. So they did this. That gives you 5/9. That's what sine squared is. So because secant u is negative, tangent u is positive, it follows that u is in quadrant 3. I like to go on and take care of that. As soon as they told it to me, figure out what that means for you. Okay? So we're in quadrant 3, so what sign do we use? For sine, negative. Okay? Moreover, because sine u is negative when you're in quadrant 3, then choose the negative square root of that, and that's where you get negative root 5 over 3. But you see, drawing the picture, when we drew the picture, it showed you were there. I mean, once you determined you were going to be in third quadrant, it had to be there. Okay? All right. It had to be a negative root 5. And knowing the values of sine and cosine enables you to get all of the rest of them. So sine is this, cosecant is its negative reciprocal, and isn't that totally wrong? The answer's right, but the middle part is wrong. They put what secant was, not cosecant. It is wrong. They should have put negative 3 over root 5. Okay, because this is negative root 5 over 3. So that should be a root 5 there. Shame, 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 okay? Whoever the graphic person was really botched that one. Okay? Then cosine, we already had determined to be negative 2/3, and secant was given. Look, this drives me nuts. Okay? That's a totally wrong answer. That's what should have been up there for cosecant. And they keep it wrong. Remember what the problem said? What they gave you. Secant is negative 5 over 3. It's not that, okay? So don't do that. I mean negative 3 over 2. I'm sorry. Negative 3 over 2. Fire the graphic person. Okay. That was given in the problem. You don't need to calculate it. Okay? It was given to you. Write it down correctly. And of course, that's reciprocal of cosine, not the reciprocal of sine. So they really botched that up. They got the second part of secant right. mess up secant completely. And that's what was given. Okay, tangent then is going to be merely sine over cosine, which you did quite correctly as opposite over adjacent. Okay, gives you the same thing. Minus over minus is plus. They told you originally tangent was plus. This confirms it. Root 5 over 2. And then the cotangent is, of course, its reciprocal, which is either 2 over root 5 or 2 root 5 over 5. Now, here's just a little hint. I think we've already said it. Let's say it again. Anytime one of your trig functions is negative, that means 4 of them are negative. Only 2 can be positive. If you're in the first quadrant, they're all positive. So in any other quadrant, you're going to have 2 positive, 3 and 4 negative. So that's another little good thing to look at and make sure you got right. Here we have the top 4 are negative, the bottom 2 are positive. Okay. Here we have example 2. Now this is a different kind of problem. By the way, there was a checkpoint there right beneath example 1, and all those audio-video solutions to the checkpoints are at larsonprecalculus.com. Okay. Here we're doing something different. We're simplifying a trigonometric expression. There's the expression. Sine x times cosine squared x minus sine x. How can we simplify that? What's usually the first thing to try? Especially if there's nothing really obvious about it. Say again? Yes, factor it, okay? I was going to ask for what the Alford word is, but you got it already, okay? Okay, factor out a sine. And what does that leave you with? Cosine squared x minus 1. Perfect. Now, that is simplified a little bit. What does that cosine squared x minus 1 kind of look like? Not quite right, but awfully close. The Pythagorean, yeah. That, and what was that? Remind me of that one. Sine squared x is equal to 1 minus cosine squared x, right? Okay, now how does that differ from this? Say again? Okay, yeah, okay. Don't worry about that. How does 1 minus cosine squared differ from cosine squared minus 1? Yeah, you reverse the subtraction. And what's another way of doing that? Yes, either multiply or divide by negative 1. So you could actually factor out a negative 1 out of that to produce this, right? But if you may factor out a negative 1 here, you must do it here. So what would that be then? So in other words, what I'm saying is, I like multiplying rather than dividing. Let's multiply everything on both sides of this equation by minus 1. Minus sine squared x is equal to minus 1 plus cosine squared x. And then we can just rewrite that as cosine squared x minus 1, right? Just reverse them back, and that's minus sine squared x. Agreed? Okay, so what can we put in place of that? Sine x is there. Don't throw it away. You're going to use it. But cosine squared x minus 1 is the same as negative sine squared x. Okay, and guess what happens if you multiply those two together? Negative sine cubed x. That's about as simple as I can get it. So we have just simplified that expression. Now notice there's no equal signs in the expression, right? So you're not solving for anything. You're just simplifying. Okay? And that's what you get. That thing simplifies to be this. I put the equal signs there, meaning that is equal to this, is equal to this, equal to this, but there's no equation to solve. We're just simplifying. Okay? All right. Does that make sense? There is a checkpoint there at the bottom of page 349. Somewhat similar but different from example 2. Sorry. Oh, before we turn the page, let's see how they did it. So I'm going to erase it all. Is it okay to erase it now? Okay. Let's see what they do. First, factor out the common monomial factor, and then use the fundamental identity. So they first factored out a sine x and left you with a cosine x minus 1. And that looked awfully close to, okay, they did it slightly differently. Then they factored out a minus 1 out of this one, which is what y'all said to do. You said divide each other one. So factor out the minus here, and that reverses the order here. So then you have a minus sign times a sine squared. Okay? Which is the same way we did it. We just did it slightly differently. Minus sine x times sine squared x will be minus sine cubed x. Simple as we can write it. Okay. Any questions on that? Whoa! They jumped to example 7. So let's go back and let's us do example 3 and 4 and 5 and 6. Okay. So let's do example 3. So we did it before. Now we're going to do it again. Factor trigonometric expression. Well, no, we didn't. We factored out a common monomial factor. We're going to factor some other things here. Okay. The first of these, this is 3a, is secant squared theta minus 1. And they say factor it. Don't use an identity, just factor it. How does that factor? Perfect. It's the difference of two perfect squares, and it factors as secant theta plus 1 times secant theta minus 1. Perfect. Okay, that was easy enough. How about this one, the B one? 4 tangent squared theta, okay, plus tangent theta minus 3. Now there's a couple ways you can do that. Well, what would be your approach to it? Would you have an approach? Or would you stay away from it as far as you could? No, we're going to approach it. Okay. How would you like to do it? You wouldn't, would you? Okay. All right. Would it help to do a little substitution? It would. So let's make up some new variable. Not brand new, I mean, just not theta. Okay? What variable would you like to use? X, why not? That's everybody's favorite. Let X equal, except when I'm grading your papers. No, okay. X equal, how about tangent theta, right? Is that okay? So what is this expression now? 4x squared plus x minus 3. Now, if I told you the factor of that, would that give you much effort? Trouble? No, not really. And we could have done the other two, but let's do it. So let's see if we can factor that. Actually, it's not a particularly easy one to factor, but it's okay. What would you try first? Okay. Huh?
Put 2x in each one.
Second.
Put 2x in each one.
Okay. What one possible factorization of 4x squared is 2x times 2x. That's perfectly correct. Okay? Now, where I look next is the sign of the last term. And what is it? Negative. That means these two signs have to be opposite. So one positive and one negative. Okay? Does it matter to you which is which? Okay, so we'll put plus here and minus there. Now, what is one possible factorization for 3? 3 and 1. So let's put 3 and 1. Okay? Now, let's see if we got a correct factorization. How do we check it? 4. Right? Okay? So 2x times 2x is 4x squared. We knew that should be right. Then we do the outers, which are minus 2x plus 6x. That would give you minus 2x plus 6x plus 4x. Wrong answer. And since we've got a wrong number, we need to change the numbers. Okay? The most obvious number change is to not do 2 times 2, but to do 4 times 1. Okay? So this time we'll change one of these 2's to be a 4 and make the other just a 1. Okay? So that will be 4x plus 3 times x plus 1. Okay? Do we know that's the factorization? No, not until we check it. So let's check it. 4x times x is 4x squared. Hey, that one worked. 4x times minus 1 is minus 4x plus 3x is minus x. Wrong again. But this time, it's not wrong by the numbers, it's just wrong by the sign. So therefore, we change the sign. Don't change the numbers, just change the sign. So we'll make the first one, it will make the second one the plus, and the first one the minus. Okay? Do we know that's going to be the right answer? Not until we check it, but we have a pretty good idea it will be. 4x times x is 4x squared. Got that. Outers is plus 4x, innards are minus 3x, that gives you plus x, and then the last is minus 3. Yes, we finally got it factored. But that wasn't our original problem, was it? What do we need to go back to? It'll be what? For tangent theta minus 3 times tangent theta plus 1. Got it. Done. Okay? Now, you can certainly do this, do the substitution and work with it that way. To me, it is easier to see. But after a while, you just think of tangent theta as being the variable. And you do the same thing with that, never even have to go to an x or something else. Okay? It's a little bit more writing because you have to write tangent x, whereas tangent theta, whereas x is real easy to write. But you don't have to do those middle 2 steps. Okay. Good deal. Let's see how they did. The A, they got secant theta plus 1 times secant theta minus 1, good for them. And this one they got 4 tangent theta minus 3 times tangent theta plus 1. They got them both right. I'm so proud of them. Okay, there are checkpoints there, A and B. Please consider doing those. All right, let's move on to example 4. All right, example 4. Another factoring. Factor this. Cosecant squared x minus cotangent x minus 3. What? Huh? You can't do a substitution there, can you? Why? They're not the same values. They're not the same functions. Got to hang this one up and move on? No, we wouldn't think of doing that, okay? So what might we do first? How? Second? Okay, how do we get them both to be the same? We use an identity, absolutely. And what identity relates cosecants and cotangents? One of your here's a hint. When you see a square, think Pythagorean, exactly. Is there a Pythagorean identity that relates cosecants with cotangents? Yes, there is. Tell me how that one goes. Equal cosecant squared. Okay, since we're using x, let me put x's in there. Okay, absolutely. So, instead of cosecant squared, we'll put 1 plus cotangent squared x minus cotangent x minus 3. Okay, now what can we do to simplify that a little bit? Second? Okay, one of the earliest things we did with simplifying expressions was combining like terms. Do you have any like terms there? 1 and a negative 3. So let's combine those two. We're going to put them at the end. So that'll be cotangent squared x minus cotangent x. And what do those combine to? Negative 2. Okay? Now you want to do a substitution or use cotangent? Huh? Name one, huh? Okay, use cotangent. Okay, and we'll do it just as if that was a variable. Okay? What's the only possible factorization for cotangent squared? Cotangent x times cotangent x. Right? And then we look where? Sign of the last term is negative, so these two have to be opposite. One's positive, one negative. You can put them in any order, I don't care. I'll put plus and minus. Now we consider the last one. What's the only possible factorization for 2? 2 and 1. You want to put them in that order? No? Which order you want them? 1 and 2, looking ahead, okay? You don't like doing all that trial and error stuff, okay? Let's check it and see if it's right. Cotangent times cotangent, sure enough, it's cotangent squared. Cotangent times minus 2 is minus 2 cotangent, plus 1 cotangent. It'll be a minus cotangent, minus 2, yes, we got it right. We have now factored that thing with cosecants in it. No more cosecants in it. They're all cotangent. Now, look up there the original example 2. When we factor out the sine x, again we had a cosine squared x, and we looked around and saw the identity. When you see that squared, think Pythagorean. Is there any way this relates to Pythagorean? And sure enough, that's where we found it. Same thing here. Okay? Now, that's a good technique when you have a square. Okay? Oh, and by the way, there was a checkpoint there. Don't forget to do the checkpoints. Now, example 5 says right off the top, see larsonprecalculus.com for an interactive version of this type of an example. Okay? So, let's do example 5. You can go and look at larsonprecalculus.com if you'd like later. See how they approach it. Here's what example 5 is. Sine of t plus cotangent t times cosine t is equal to, this is not an expression, this is an equation. Oh, I'm sorry. Forget that. It is an expression. Okay? Don't look at the book. Don't think of a big black horse. Okay? What are you thinking of? Okay. Now, that's what we're asked to simplify. That. Don't look at the book. Now, what's wrong with this picture? You don't just have two trig functions, you have three trig functions. Now, here's a technique for this. And none of them are squared, so you can't think of a Pythagorean identity, or at least not yet. So here's my little rule. When I can't think of anything else to do, here's my little technique. Get everything in terms of sines and cosines. Okay? So let's do that. Sine is already in terms of sine, okay? So just write it down. Sine t plus, what is cotangent in terms of sine and cosine? Cotangent t, I'm sorry, cosine t over sine t. And then multiply that by cosine t. Okay? Now what does that turn out being? Sine t plus cosine times cosine is cosine squared t, right? Over sine t. Right? Oh, y'all remember the little song, 10 Little Indian Boys? 10 Little Indian Boys. How they go? Oh, how does it go? Something about something, and then you're down to 9, and then something happens, you're down to 8, then after you're down to 7. You know, it's sort of like the things you sing in buses on long trips, right? I don't remember how it goes now. Well, I know it was there. Okay. So we were at 3, we're down to 2. So went from 3 Little Indian Boys to 2 Little Indian Boys. Okay. Now, sorry, it's sexist. Okay. What do you do with that? If you had, make up a number. 2, make up another number. 5. So if you had 2 plus 5 over 2, how could you combine those? 2 plus 5 over 2. Common denominator, what is it? 2. And then you'd want to put a 2 under here, but if you put a 2 under here, you also have to multiply by 2, right? Okay, so that's what we're going to do here. Instead of 2's, we have a sign in the denominator, right? So what are we going to do? Put a sign in the denominator, but if you multiply that, you have to put a sign in the numerator. Well, what's sine times sine? Sine squared. Okay, so what we have now, since you have the 2 common denominators, you can add the numerators, keep the denominator, right? So now we have a sine squared t plus cosine squared t over sine t. Agreed? Okay. Now, my question to you is, what is sine squared t equals cosine squared? 1! Oh, look at that. So this becomes 1 over sine t. Now that's simplified some, but we can even do one better. What is 1 over sine t? Say again? Nope. Cosecant t. So this is equal to cosecant t. So we started out with 3, we went down to 2, we manipulated them, got it down to 1, and then changed the 1 to one that wasn't even in the first 3 to begin with. Okay? But that's about as simple as you can get, right? Make sense? These are kind of fun, aren't they? Sort of like a puzzle or something. All right. So that was example 5. And there's an audio-video solution, audio-video solution for that. Checkpoint. There is a checkpoint for this problem, which also has audio-video solution. Okay, I think now, no, we still got example 6 to go, don't we? And there was a pause there. I hit the wrong button. Okay, we'll erase all those and do example 6. Perform the addition and simplify. Sine theta over 1 plus cosine theta plus cosine theta over sine theta. Okay. Perform the addition and simplify. How do we add fractional forms? Common denominator, what would it be? Sine, yeah, you just have to multiply them together. So, how do you get this one to be that? Multiply by sine, right? But if you multiply the denominator by sine, you got to multiply the numerator by sine as well, so that makes sine squared, right? Now over here, we already had a sine, so we have to multiply with 1 plus cosine theta. Okay? So that means we multiply the numerator by 1 plus cosine theta. Okay? Now, what we have now is a sine squared theta plus, now I'm going to multiply that out, cosine theta plus cosine squared theta. See what I did? All over that common denominator. Sine theta times 1 plus cosine theta. Now notice what I didn't do. I didn't multiply those out, okay? Because I don't see how it's going to help us. But we did need to do that up top. Now, one reason we did it up top, notice what we've got now. Sine squared theta plus cosine squared theta, what's that? Theta? 1. So you got 1 plus cosine theta, don't you? Oh, look at that. These two becomes 1, and you get 1 plus cosine theta over sine theta times 1 plus cosine theta. And guess what you can do now? Divide them out. What does the numerator become? 1. And what's 1 over sine theta? Wasn't very long ago we had it. That's cosecant theta. Boy, they must like cosecant theta. They've had 2 in a row that came out that was right. Ah, the other one was t, sorry. Okay. Make sense? Did you ever think that mess up there would just come out to a single trig term? It happens. And so sort of these fundamental identities are kind of fun, right? Okay. So that was our example 6, okay? Now I'm going to step through the example 2 steps. And here's example 7. How we do it? Ooh, we may be able to squeeze it in. All right, what we want to do is rewrite 1 over 1 plus sine theta so it is not in fractional form. Now, I usually don't like to rewrite, but I almost have to now because it's in the middle of a sentence. So we're going to start with this, 1 over 1 plus sine x. Now, we're going to need to rewrite that so it's not in fractional form. Now, does anything about that expression look maybe vaguely familiar to something you've done in the past? Okay, probably not. I want to throw a word out. Conjugate. Oh, what's a conjugate?
When you have like, you just change the sign. Right?
Second?
You change the sign so it's like 1 minus.
Yes, the conjugate of that denominator would be 1 minus sine x. And frankly, when you have something that can be expressed as a conjugate in there and can't think of anything else to do, why not multiply by the conjugate? Because we did that when we were rationalizing denominators. We did it when we were doing complex numbers. That's always, and we did it when we were just factoring or multiplying. Yeah, so let's multiply by the conjugate, okay? So the conjugate, as you said, was 1 minus sine x. But if you multiply the denominator by that, what had you better do? Multiply the numerator by 1 minus sine x as well. Okay? Now, the numerator becomes 1 minus sine x. Okay? What's the denominator become? One minus sine squared x. Very good. Now, frankly, that looks like it's further from being not in fractional form than what we had to begin with. Except what is 1 minus sine squared x? Cosine squared x, a good old Pythagorean identity here. So now we have 1 minus sine x over cosine squared x. Now here's something, folks. Anytime you can get a denominator to be a monomial, up here it was a binomial. Now it's a monomial. Sure, it's squared, but it's easier to deal with. So now we can break that up, sort of do the reverse of subtraction. Other than finding the least common denominator, let's just split them into the same denominator, right? So this will be 1 over cosine squared x minus sine x over cosine squared x. Okay? Now both of those are in fractional form, so it really doesn't look like we've done much to get better, have we? Except, what is 1 over cosine squared? Secant squared, exactly. Secant squared x minus, well, we got rid of one denominator, but what else, how could you express this? Let's factor that denominator and make that sine x over cosine x times 1 over cosine x. Isn't that fair? Well, what's sine x over cosine x? Is what? Sine x over cosine x? What did you say? Tangent. Okay, I can't hear well. Tangent x, and what's 1 over cosine x? Secant x. Look at that. Not in fractional form. No denominators. We lost them all. Okay? Yep. We just rewrote that so it's not in fractional form. Because secant squared is in fractional form. It's 1 over cosine squared. Tangent is sine over cosine, and secant is 1 over cosine. But guess what? We got them all, the denominators gone. All right, to erase? Okay. Let's see how they did it. Okay. They started with a Pythagorean identity, which there was no real reason to do that. I prefer, let's start by multiplying by the conjugate, okay, which ultimately they did. And then they said, oh, look at this, we get a Pythagorean identity. But they started with that and say, now work back. Who knew, okay? But if you just do a step, well, that looks like half of a conjugate, multiply by the other half. And sure enough, you get that. And that becomes 1 minus sine x over cosine squared x, exactly like we did. And make that 1 minus cosine x over sine minus 1, or sine x over cosine squared x. That's secant, well, that's 1 over cosine squared x minus sine x over cosine x times 1 over cosine x. Same way, different order. And that would be secant squared x minus tangent x secant x. Done. Just like we got. Whoa, that's the end of the section? I think not. Yeah, we got 2 more examples. We'll begin there next time. But I'll start with 5.2 because these 2 aren't on 5.1. So, made pretty good progress today. We got almost through with 5.1. All right, any questions? You all got your test? Makes for a fun weekend, doesn't it? Have a great weekend. Working trig problems will make it a great weekend, right? All right.
Have a good
What's that?
Oh, we're gonna go play volleyball with our high school friends in the morning.
So again, have y'all got a team?
No, we're just like the girls we used to play with in high school.
Yeah.
We're gonna go meet them and play.
Yeah, sounds great.
Yeah.
All right, have a good weekend. Thank you.
I think if we go for tonight too. So make some
Did both of you do both things, or one of you specialize as spiker and the other setter, or what?
I'm a setter. I'm like a defensive.
You're what?
I'm a defensive.
Defensive. So you were a digger, huh? Yeah, okay, good deal.